All right, let's dive into a really fascinating energy puzzle today. It's all about what holds one of the most common things on Earth together. Yep, table salt. And trust me, the answer is probably not what you're thinking.
So what really holds a single grain of salt together? You might have a simple answer in your head, but what if I told you it's more like a high-stakes business deal? There's a risky upfront investment, a little bit of a cashback rebate, and then a huge final payoff. It's this whole chemical drama that explains why these atoms stick together so tightly.
Okay, so it all kicks off with a simple electron transfer. In an ionic bond, like the one we see in sodium chloride, it's all about giving and taking. You've got a metal atom, in our case sodium, and it gives away one of its electrons. And then you have a nonmetal atom, chlorine, which is more than happy to snap it up. This little exchange creates charged particles, which we call ions. But here's the catch. This simple trade, it comes with an energy cost.
So, to really get why this bond forms, we have to become energy accountants. We've got to follow the money or, well, follow the energy. Think of it exactly like a business transaction. First up, we've got to spend some energy just to get this whole thing started. So our first cost is something called ionization enthalpy. Now, that sounds technical, but it's actually a simple idea. It's just the amount of energy you have to pump in to pull an electron away from a neutral atom. And it's not free. You absolutely have to pay this energy price.
Let's look at our sodium atom. It starts off as a neutral atom just minding its own business in a gaseous state. To get the process going, we need to supply enough energy to literally rip that outer electron away from it. And when we do, it becomes a positively charged sodium ion.
And just how much energy are we talking about? A pretty hefty 495.8 kilojoules for every single mole of sodium atoms. That is a significant upfront investment of energy. And you see that little plus sign there? That's super important. It tells us that this is energy we have to put into the system.
Okay, so that was our cost. Now let's look at the other side of this deal. When our chlorine atom gets that electron, there's another energy change, and this one is called electron gain enthalpy.
So here's what's happening. A neutral chlorine atom, also in its gaseous state, captures that electron that sodium just gave up, and in doing so, it becomes a negatively charged chloride ion. Now here's where it gets really interesting. Look at the sign on that number. It's negative. This is huge. It means that when chlorine grabs an electron, energy is actually released. It's like getting a small energy rebate or a partial refund on our investment. But, and this is a big but, if you look at the numbers, that 348.7 kilojoule rebate doesn't even come close to covering our initial cost.
All right, so let's do the math. We've paid a big cost. We've gotten a little rebate, so where does that leave our energy balance sheet?
Well, when you subtract our little rebate from that big initial cost, we are still deep in the red. It costs a net total of 147.1 kilojoules of energy just to create 1 mole of sodium ions and 1 mole of chloride ions, assuming they're just floating around separately. This whole process so far is endothermic. It absorbs energy.
And this right here is the central puzzle. Think about it. Nature always favors lower energy states. Things don't just happen if they cost energy. So if it takes a net input of energy to even make these ions, why on earth does sodium chloride even exist? Why isn't salt just constantly falling apart? There has to be something we're missing.
And that missing piece, that big secret, has nothing to do with the individual ions at all. The solution, the massive payoff that makes this whole risky investment worthwhile, is what happens next when these ions finally come together.
And here it is. The solution is this beautiful structure, the crystal lattice. You see, once those positive sodium and negative chloride ions are created, they don't just drift apart. No way. They are powerfully magnetically attracted to each other, and they snap together into this perfect, repeating three-dimensional grid. Look at how each positive ion is perfectly surrounded by negative ions, and each negative ion is surrounded by positive ones. This locks the entire structure into an incredibly stable formation. Now, the energy that gets released during this spectacular act of self-assembly has a name. It's called lattice enthalpy. And folks, this isn't some small rebate. This is the jackpot. This is the huge energy dividend you get for creating such a stable, ordered structure.
And for sodium chloride, how big is that payoff? It is enormous. A whopping 788 kilojoules of energy are released for every mole of salt that forms from its gaseous ions. This massive release of energy is what drives the whole process forward. This is the reason that initial energy investment was totally worth it.
Okay, so let's look at the final books. Let's tally everything up. When we put all these numbers together, we can see exactly how this incredible payoff solves our entire puzzle.
So here's the final breakdown. Step 1, we pay our initial cost of almost 496 kilojoules to make the sodium ion. Step 2, we get that small rebate of about 349 kilojoules when the chloride ion forms. But then, step 3, we get that colossal payoff of 788 kilojoules released when the lattice forms. So what's the grand total? A huge net release of energy, over 640 kilojoules per mole. That giant negative number is the telltale sign of a superstable compound, and it's the final answer to our puzzle.
So let's wrap our heads around this whole energy story. The main takeaway is that just forming the ions is only the beginning, and weirdly enough, it can actually cost energy. The real magic, the reason ionic compounds like salt are so incredibly stable, is that immense energy payoff you get when the crystal lattice forms. That final, huge energy release totally wipes out the initial costs and makes the whole thing a slam dunk, energetically speaking.
And that leaves us with one last question to chew on. We've just seen how this delicate energy balance works for the simple cube shape of salt, but every ionic compound has its own unique set of costs and payoffs, right? So how do all those different numbers end up creating the incredible and sometimes wildly different crystal shapes we see all over the world? Now that is a puzzle for another day. Thanks for joining me on this one.